Okay, so today we're going to be talking about the mean value theorem for integrals, and we're also going to be talking about the average value of a function. Now these two things are very much related, and so you're going to see a lot of crossover, and actually we can use one to derive what the other one is. So let's go ahead and start off with the mean value theorem. For integrals. Mean value theorem for integrals. Now, I'm just going to go ahead and give it to you initially. But before I do that, I want to sketch it out. This is one of those things that conceptually is way easier to understand if you can visualize what is going on. And so here we've got our xy axis, x, y, and we've got some generic function f of x. And so if you remember, if we're looking at an interval here from a all the way over here to b, what we're solving for is the area underneath this curve. And so the mean value theorem basically says, okay, there's some point here, I'm going to draw mine right about here, some point C, where basically I can draw a box. I'm going to switch over pens here so that my box makes a little bit more sense. And so I can basically draw a box here, and the area that's in the red box is exactly equal to the area underneath the curve. And once again, I'm going to use a highlighter, show us that we're talking about the area underneath the entire curve. Okay, so basically the green highlighted area and the area in this perfect box that I drew, this absolutely perfect box that I drew, is going to be 100% the same. And this kind of makes sense because you can say, okay, well, somewhere I can put this point, I can draw this line. Basically, I know what my width is here, and so if I know what my total area is, I can calculate some height and then figure out where that height is on that f of x function. And so to put it in math speak, mean value theorem here's the mean value theorem. So basically, f is continuous on the interval a to b, which is the same thing when we were doing definite integrals. So we have some function, f is continuous, a comma b, which means it can have sharp turns, but it can't have any jumps or gaps. So basically, somewhere in here, in between a and b, there exists a number, and we're going to call it c. Exists a number, and it's going to be lowercase c, such that, remember that c is somewhere in between a and b. Basically, so we have our definite integral of x, or over our entire sort of area here. That's what we're calculating. So the area under the curve is going to be equal to f of c times b minus a. And if I look at what I've got up here, that's exactly what the area under this curve is. So the area under the curve would be the stuff on the left right here, so the green highlighted area. This f of c times b minus a, that's exactly the area of this rectangle here, this little box that I drew. So in this case, I've got c right here. Well, somewhere on this line, right, on the function, this point is going to be f of c. I'll go ahead and label that f of c. And then, so that's going to be the height of the box, and the width of my box, or the length, in this case, is going to be b minus a, so right here. So basically, I can say this green highlighted area and is going to be exactly equal to somewhere on this box. I'm finding that average function, or the mean value function. Okay, so that's the mean value theorem. Let's draw a line there. Let me shift things up. So now we're jumping right into the average value of a function. And I didn't want to put any examples here of the mean value theorem because it's going to become really obvious as to how these two things are related. And so where the mean value theorem is applied is in the average value of a function. Okay, so we've got the average value of a function. This is what we're looking for. And anytime there's an application of what an integral is, there's also the application of what the average value is. And in the second example that I'm going to go through, it gets a little bit crazy, but it's actually quite cool. And it's something that is real world. It's an application of calculus. It's an application of where you would use these integrals and mean value theorems and average values. So basically, the average value of a function, if I take this function right here and I solve for f of c, that's all I'm doing. And so if I gave you this, right, so treat this like a constant, and b minus a, that's just a constant. If I said solve for f of c, what you would do is you would say, okay, I'm just going to divide both sides by b minus a, divide both sides by b minus a, or multiply by 1 over b minus a, right? And that's exactly what I'm going to do. So the definition of the average value of a function follows the mean value theorem exactly, except I multiply both sides by 1 over b minus a. And then over on this side, I get the exact same thing. So from b to a over the interval, f of x dx is going to be equal to, and because I multiplied by 1 over b minus a on this side, that sort of cancels out, just becomes 1. This is going to be some average value there. So basically what this f of c is telling me this is the average value of the function. Okay, so if you want to visually think about, okay, so this is actually, I know I shaded it in green, so imagine it's like a hill or the terrain or something like that. It's basically asking you, okay, so what's the average value of the terrain? But not quite, because here, in this case, I'm actually talking about the area underneath the terrain, right? So here I've got some data. I'm basically just looking for the average value. You'll see this a lot in statistics, in higher level statistics, where they're using calculus and derivatives to be able to calculate things like means and averages and areas under curves. So let me jump right into an example using the average value of a function. So here I'm just going to give you a regular definite integral, and I'm just asking you to find the average value. Of, in this case, it's going to be f of x is going to be equal to 3x squared minus 2x. And of course, because it's a definite integral, you need that interval where you're looking at over the interval 1 comma 4. So hopefully by now, you guys can automatically take this and really, really quickly just jump into and say, okay, well, I know one of the things that I'm going to be doing is going to be going from 4 to 1 of 3x squared minus 2x dx. And also, you should be really, really comfortable being able to solve what this definite integral is. Well, if I'm using this average value of a function, right? So that's this piece right here. But I can't forget, I've got to just say I've got to multiply by 1 over b minus a. And of course, this interval right here goes from a comma to b. So b minus a, or I should say 1 over b minus a, is going to be equal to 1 over 4 minus 1, which is equal to 1 over 3. Okay, so that's just going to jump out front right here. So I'm just going to say this is going to be 1 over 3 times this whole thing. So whatever the area is, so think about what we're doing here. So here I've got the area under the curve. Basically, I'm just taking a third of it. And remember, this number is going to change. It's not always going to be 1 over 3. This is going to be based off of the interval. Basically, I'm just taking the entire area. I'm taking a third of it, and then my problem is done. I know what the average value of the function is. And so let's go ahead and just keep going with this. So I've got my 1/3 that's going along for the ride. Hopefully, once again, you guys are super comfortable doing this antiderivative here. So if I do x plus 1 over, so I've got 3 times x to the 2 plus 1 divided by 2 plus 1 minus 2 times x to the 1 plus 1 over 1 plus 1. And then square brackets, and I go from 4 to 1. Okay, so this is going to become 1/3 still out front, going along for the ride. Here I've got 3 over 3, so I just get, this is going to be x cubed. And here I've got 2 over 2, so I just get x cubed minus x squared. And real quickly, I particularly like, if I do this one super, super quick, I particularly like just doing a real quick check of it before I go on in case I made a mistake. So I take the derivative of this, and I go, okay, so that's going to be 3x squared minus 2x. Sure enough, that's exactly what I've got here. So just even without even needing to write that down, I can do my super quick check, double check that I'm going in the right direction. Okay, so this one, So I can say 1/3 times, now I'm going to do my f of b. In this case, b is going to be 4. So I can say 4 cubed minus 4 squared minus, and in this case, my f of a is going to be 1 cubed minus 1 squared. Now 1 minus 1, that's just going to be equal to 0. So I can just ignore that one. And I've got 4 cubed minus 4 squared, which is going to be equal to 1/3 times 64 minus 16. Once again, that becomes 0. And I just get 48 divided by 3, which is just going to be equal to 16. That's going to be the average value of this function. Now, if I wanted to take a look at this function, okay, I'm going to show you what this function looks like. Feel free to pause this and put this in your notes, but this is a figure from the book, basically just illustrating what it looks like. So here I've got this function, and here it's plotted out over an interval from 1 to 4, and you can see it gets pretty big because it's a third order polynomial. But it goes up, and we're just looking for the average value. And sure enough, it happens right there, and we get an average value of 16. Okay, so now let's go ahead and take a break, or take a step back, and take a look at an application. When would we ever use this? And this isn't just an application of the average value of a function, but it's more an application of these integrals and antiderivatives in general. And that's when we're trying to calculate the speed of sound. So at different altitudes in the atmosphere, the speed of sound varies. Okay, so it travels at different speeds. In meters per second, there's a huge function that this thing can model by, and I'll just do the first 3. Okay, so basically, you can say s of x, so that's going to be the speed of sound with respect to altitude. X is going to be altitude in this case. And so it's modeled by this piecewise function, minus 4x plus 341, and that's over the interval because it's a piecewise, x to 11.5, from 0 to 11.5. And the altitude is in kilometers here. So x is in kilometers. So from 0 to 11.5 kilometers, this can model what the speed of sound looks like. And it's also equal to 295. So it stays constant between 11.5 kilometers and 22 kilometers. And then it goes 3/4 x plus 278.5, another linear function between 22 kilometers and 32 kilometers. And then there's a couple more of them here. So a couple more linear functions, once again piecewise functions, plus 254.5. And so we can say that that's from 32 to 50. So we're getting pretty high now. And then now we've actually got a negative linear function, so it goes down again. X plus 404.5, 50 kilometers to 80 kilometers. Okay, so we have this huge piecewise function. So s of x is going to be equal to this entire thing, all of these, based on the speed of sound. And if you wanted to plot this out over this interval, let me zoom in here. This is what it looks like. So you can see we do have a continuous function because I can start at one end and draw the entire curve without ever picking up my pencil. Okay? And so the question is asking, what is the average speed of sound? And so we can see that sure enough, like if it was a constant line, that would be really easy to figure out what the average speed of sound is, right? So here's the speed of sound in meters per second, altitude in kilometers, but it's not really easy to figure that out as things are. And this is very much a real world problem, okay? So let's see how we would do this. Okay, so we have a piecewise function using some of the properties of definite integrals. We know that we can sort of take the integrals of each one of these separately and then multiply it by that particular, and then add them together to sort of get what the total area under the curve is. So what that would look like is, okay, so I'm first going to take the integral. I'm going to take the definite integral of just this piece right here, okay? So that's going to be my first interval right here, finding the area underneath the curve, okay? Here's going to be my second interval right here. This is that constant one, okay? So now from 0 to, about 11.5 to 20, there we go. And then there's going to be my third interval, once again, breaking it up, finding all these different areas, Okay, so once I find the area of each individual little piece, I can put them all together and then basically just divide by the entire interval and figure out what my average is. So I'll just do the first couple here to get us off. You guys can do the other ones. I'll give you the answer. You guys can do the other ones if you want to double check me. Basically, so we've got since we're going to integrate this, I'm going to go from 11.5 to 0 of s of x. Now I know what that is. I know s of x over that interval is just going to be minus 4x plus 341. So now I'm just looking for that first area, right? And so I can basically just do this real quick. Oops, I forgot one thing here. Never forget the dx is going to be equal to, now I can do this, it's going to be negative 4x is going to become negative 2x squared when I do the antiderivative. Plus 341 is just going to be plus 341x, right, from 11.5 to 0. Once again, you can plug in your f of b, subtract f of a, and this is just going to be equal to 3657. Next one, this one's easy, 295 constant times dx. And this time our intervals are going from 11.5 to 22. Once again, just reading right off, 11.5 to 22, this is the function, 295 dx. This is easy. 295 just becomes 295x when I do the antiderivative from 22 to 11.5. Nothing to it. So this is just going to become 3097.5. And the last one that I'll do is going to be from 32 to 22. Once again, just sort of ticking these off one at a time. So we did this one, now we're doing this one. Okay. And so this one is going to be 3/4 x plus 278.5, that dx. And if I do the integral, this is just going to become, or sorry, if I do the antiderivative, this is going to become 3/8 x squared plus 278.5x from 32 to 22. Once again, you can do the math here real quick. You end up with 2,987.5. Now the other two, so that takes care of that one. The other one is going to be equal to 5688 total, and the last one is going to be 9210. So all I need to do is add each one of these separate, oops, I went off the page here. Each one of these separate values, each one of these separate areas underneath this curve. So from here, that's going to be 1, 2, 3. Here's the other one, 4, and here's the last one, 5. So adding all the areas, so I have the total area underneath the curve. And so basically I can say from 0 to 80, and where did I get 80 from? Well, that's the interval that we're talking about here. So an original problem, 0 to 80. So if I'm going from 0 to 80 of s of x, this entire piecewise function, continuous, but definitely piecewise, I know the entire area is 24,640. Now, in order to figure out what the average speed of sound is, I just need to take this and multiply it by my interval. And so I could say 1 divided by, and remember our interval in this case, it starts here at 80, or starts here at 0 and goes to 80. So I'd say 80 minus 0. So in this case, I'm going to get 1 divided by 80. The integral of 80 to 0, s of x dx, which I already know what this is 24,640. And so basically I can say this is 24,640 divided by 80, right? And this is going to be equal to 308 meters per second. And this makes sense. If I look at my original plot here, or my original graph, sure enough, I'm on the scale from about 285 at the lowest to 340 somewhere in here. And sure enough, the average is going to end up being right about here. So if I drew a box right here, this area is going to be exactly equal to that area. Looks pretty good. Awesome. All right, I'll see you guys in class tomorrow.